Okay, so we're diving into this paper that everyone's talking about.
Yeah, it's pretty mind-blowing.
It tackles, like, one of the biggest challenges in mathematics, right? Hilbert's sixth problem?
Hilbert's sixth problem, yeah, been around for over a century, puzzled mathematicians for, like, forever.
Feels kind of wild that they're making progress on this now.
It is. And this paper, it claims to make significant progress.
Yeah.
Bridging this gap between, the super tiny world of particles and then the big world that we live in with fluid dynamics.
It's like connecting Newton's laws to things like the Navier-Stokes equation.
Exactly.
Which is crazy when you think about it.
It is mind-boggling.
Like, how can you even start with something that complicated?
Well, they've done it. They've actually created this rigorous mathematical framework.
No way.
It shows, under certain conditions, how you can go from those tiny particle descriptions all the way to describing fluids.
So they've basically built a mathematical bridge between these two worlds.
They have. It's a big deal.
Okay, so for those of us, like, in the AI and ML world, what are the key takeaways from this?
So in the first minute, let me summarize the paper's key insights. Mathematicians have now created a rigorous mathematical proof showing how, under specific conditions, the behavior of a large number of tiny colliding particles can be accurately described by the Boltzmann equation. This equation, in turn, can be used to derive the equations that govern fluid dynamics, such as the Navier-Stokes equation.
Got it. So it's not just about fluids, right? This research seems way bigger than that.
It is. The implications are huge. Think physics, engineering, even AI.
Wow.
It provides a deeper understanding of how macroscopic phenomena emerge from microscopic interactions, potentially leading to more accurate simulations and predictions of fluid behavior.
So we're talking, like, climate modeling, drug discovery, even understanding financial markets, right?
You got it. You're catching on quickly.
I'm trying. This stuff's pretty dense.
Now, are you ready to really get into how they actually achieved this?
Let's do it. But before we get lost in the weeds, can you just remind me what exactly Hilbert's sixth problem asks for?
Sure. So Hilbert basically challenged everyone, all the mathematicians out there, to develop this really solid mathematical framework that connects the microscopic description of matter, like a system of particles constantly bumping into each other, to the macroscopic description of fluids, things governed by, those famous equations like the Navier-Stokes.
So it's about finding a way to translate, like, the language of particles to the language of fluids.
Exactly, yeah, but where do you even begin?
Seriously, it's so complex.
Well, they break down this challenge into two major steps: the kinetic limit and the hydrodynamic limit.
Okay.
The kinetic limit focuses on how the individual motions of particles, each one governed by Newton's laws, can be described statistically as, like, this collective.
So instead of tracking every single particle, you zoom out and look at, like, the big picture trends in their movement.
You got to think of it like analyzing the movement of a swarm of bees. You don't need to follow every single bee, right? You just need to understand how the swarm behaves.
Makes sense.
And what equation emerges from this kinetic limit? It's the famous Boltzmann equation.
Ah, yes, the Boltzmann equation.
Describes how the probability distribution of particles in a fluid evolves over time.
So it gives us, like, a snapshot of how those tiny particles are behaving as a group.
Exactly. You're with me so far.
I think so. What about the second step, the hydrodynamic limit?
Okay, this is where it gets really cool.
Okay.
This hydrodynamic limit is all about connecting the Boltzmann equation, which still deals with those particles, to the equations of fluid dynamics, like Navier-Stokes, which treat the fluid as one continuous substance.
So it's like the final step, right? Going from particles to, like, a smooth, continuous fluid.
You got think of it like taking a blurry picture and making it super sharp.
But didn't, like, someone already make some progress on this back in the 70s?
You're thinking of Oscar Landford.
Yeah.
He made a huge breakthrough back in 1975. He actually proved that the Boltzmann equation could be derived from particle dynamics, but only for really short periods.
Ah, so this new research builds on that.
They did. They actually managed to extend Landford's work to, like, any time scale you can imagine.
Wow.
They've shown that this connection between particles and fluid dynamics holds true not just for a moment, but, like, forever.
That's huge. They filled in that missing piece.
They did.
Okay, what else is new in this paper? What else did they find?
Well, they go beyond the Boltzmann equation.
Okay.
They actually show how to use their results to get other important equations in fluid dynamics.
Like what?
Things like the incompressible Navier-Stokes-Fourier system and the compressible Euler equation.
Wait, are those the same equations we use to, like, model airflow over an airplane wing?
Yes and no.
Okay.
The Navier-Stokes equations, they come in different flavors, right? The incompressible version applies when we're dealing with fluids where the density doesn't change much as they flow, like water in a pipe.
Got it.
Pretty much the same density throughout.
Okay, so that's like a nice steady flow.
Yeah, and then there's the compressible version for when those density changes are like really important, like the air flowing over an airplane wing where the air compresses and expands.
Right, that makes sense.
And the Euler equation, that's a simplified version, often used for like super high-speed flows.
Okay, so these theorems cover like a lot of fluid dynamic scenarios.
They do.
It's pretty amazing that they got both those versions, incompressible and compressible, from the same like particle model.
It is. It's impressive work.
Now, before we move on to those specific theorems, can you explain this Boltzmann-Grad Scaling Law thing you mentioned earlier?
Sure.
Like, what does it mean for a system to be dilute?
Great question. So the Boltzmann-Grad Scaling Law, it's like a way of adjusting the settings on our particle system as we like zoom out to look at the bigger picture.
Okay.
And a dilute system, that means the particles are really far apart compared to their size, so they're not always bumping into each other.
Okay, so like a sparsely populated dance floor where collisions are rare.
Yeah, and as we apply this Boltzmann-Grad scaling, we kind of shrink the particles down, but we increase the number of them at the same time, so we keep the density the same, but make those collisions happen more often.
Okay, that makes sense.
So as those particles get smaller and more numerous, their individual movements become less important, and their collective behavior, that's what starts to dominate.
So that's how we start to see, like, the fluid properties emerge.
You got it.
It's like looking at a painting from far away. Up close, it's just brush strokes, but from a distance, it all blends together.
Perfect analogy.
Okay, I'm ready to hear about those specific theorems. Let's unpack those.
Okay, let's do it. But first, maybe a quick recap of what we've covered so far.
Yeah, I think a recap would be helpful before we dive into those complex theorems.
Sounds good. All right, so just to recap quickly, Hilbert's sixth problem, right? Connecting the motion of those tiny particles to how fluids behave as a whole.
Exactly. We talked about that kinetic limit, zooming out to look at all those particles together statistically using the Boltzmann equation.
Right, and then the hydrodynamic limit, connecting the Boltzmann equation to those fluid dynamics equations like Navier-Stokes.
Yeah, which I'm sure a lot of our listeners are familiar with.
Yeah, and of course we discussed Landford's work from back in the 70s and how this new research takes his proof even further to like any time scale.
So much further. It's amazing.
Yeah, now let's get to the core of this paper, those specific theorems.
Okay.
Theorem 1, this is a big one, it establishes a rigorous derivation of the Boltzmann equation, but for a system of hard spheres on a torus.
A torus, like a donut shape. Why a torus?
Yeah, it's a clever way to model a system with those periodic boundary conditions, you know? Like in a video game where if something goes off one side of the screen, it pops up on the other.
Oh, okay. So it's like an infinite repeating space.
Exactly. Simplifies the math, but it does create some unique challenges.
Like what?
Well, for one, the number of collisions between a fixed set of particles can become unbounded on a torus. They can just keep bouncing off each other forever.
That sounds like a nightmare to analyze.
It is, but they came up with this really smart concept called long bonds.
Long bonds?
Yeah, these are collisions that happen between particles that are separated by a large amount of time.
Yeah.
By focusing those, they filter out all the noise from the countless other collisions that don't really matter as much for the overall fluid dynamics.
So it's like finding the signal in the noise.
Exactly.
Okay, back to Theorem 1. It derives the Boltzmann equation for this torus system, right?
Right. And the key part is it does this for arbitrarily long times, which is super important for linking it to fluid dynamics, because those equations describe how fluids behave over time.
That makes sense. It's like laying the groundwork for connecting those two worlds for any amount of time.
Yep.
Okay, what about Theorems 2 and 3?
This is where it gets really exciting. These theorems show how to derive two really important fluid dynamics equations from that microscopic particle system.
Okay, which ones?
The incompressible Navier-Stokes-Fourier system and the compressible Euler equation.
Wait, so like the actual Navier-Stokes equations we use to model things like airflow?
Yeah, sort of. The Navier-Stokes equations come in a few different forms.
No way.
The incompressible version, that's for fluids where the density doesn't really change much as it flows, like water in a pipe.
Okay, like a nice steady flow.
Exactly. And then you have the compressible version for when those density changes are really important.
Like with the airplane wing.
Yeah, where the air compresses and expands all over the place.
Right, makes sense.
And the Euler equation, that's a simplified version, often used for those really high-speed flows.
So they covered a lot of ground with those theorems.
They did.
It's impressive that they got both those versions, incompressible and compressible, from the same model.
Yeah, it's amazing work, really.
How do they even go about proving these theorems?
It gets pretty technical, but it involves graph theory, analysis, probability. They basically create this map of all the possible collisions using something called layered cluster forest and layered interaction diagram expansions.
Okay, those are some serious terms. Can you break that down a bit?
Sure, think of each particle collision as like a node in a network, and the lines connecting those nodes, those are the paths of the particles between collisions.
Okay.
So they're basically building this complex network that shows all the different ways these particles can interact.
Like the social network of these particles.
Yeah, exactly. And they use all these fancy mathematical tools to analyze that network to figure out which collision patterns are the most likely and how those patterns contribute to the overall flow of the fluid.
So they're analyzing the traffic patterns of these colliding particles.
Exactly.
Okay, what about that cutting algorithm you mentioned?
Yes, that helps them manage the complexity of the whole thing. Remember the torus and those potentially infinite collisions?
Yeah.
Well, the cutting algorithm breaks those complex patterns down into smaller, manageable units so they can analyze even those crazy scenarios with tons of collisions.
It's like dividing a huge puzzle into smaller pieces.
Exactly. And by looking at those smaller pieces carefully, they can put together the bigger picture of how the whole particle system changes over time and how that connects to fluid dynamics.
That's really clever.
It is.
But I'm still a bit confused about how they use this map of particle interactions to actually prove their theorems.
So a big part of their proof is about estimating the probability of different collision events.
Oh.
They use that cutting algorithm and the long dawn concept to find the most important collision patterns, and then they use integral estimates to figure out how likely those patterns are to happen.
So they're calculating the odds of different things happening.
Exactly. And by carefully analyzing those probabilities, they can show that the Boltzmann equation accurately captures how the particle system evolves, even over very long periods.
So they're connecting the randomness of individual collisions to the predictable behavior of the fluid as a whole using probability.
Precisely. And it's that rigorous analysis combined with their techniques for dealing with that torus that lets them establish the validity of the Boltzmann equation and connect it to fluid dynamics.
Okay, it's all starting to come together now that they've created this new framework for understanding how all those crazy particle collisions lead to the smooth flow of fluids.
Exactly.
But now we have a bit of a paradox, right? We know that those individual particles, governed by Newton's laws, are time reversible.
Right.
Like watching a movie in reverse. But those fluid dynamics equations, like Boltzmann, they're not time reversible. You can't unmix ink that's spread out in water.
That's a great point, a really fundamental question. How does time irreversibility come from time reversible laws?
Yeah, it's mind-boggling.
It is, but this research might offer some clues.
You're saying it could help explain the arrow of time?
It's too early to say for sure, but their work suggests that it all comes down to entropy. Yeah, the measure of disorder in a system. Think of that ink drop spreading in water. At first, it's all concentrated, low entropy.
Right.
As it spreads out, entropy increases.
And you can't reverse that easily.
Exactly. So maybe the emergence of time irreversibility at the big level is tied to this increase in entropy.
So this paper is connecting some really deep concepts here.
It is.
We've covered a lot. The theorems, the torus, the long bonds, the cutting algorithm, even the arrow of time. Maybe we should take a break and recap all this before we move on to the implications for AI and other fields.
Yeah, good idea. A little consolidation never hurts.
All right, so let's just recap everything we've learned. We started with Hilbert's sixth problem, bridging that gap between the microscopic world of particles and the big world of fluids.
Yeah, and we dove deep into this paper that really pushes the boundaries, providing that rigorous mathematical proof connecting particle dynamics to those fluid dynamics equations like Navier-Stokes.
Right, those two key steps, the kinetic limit and the hydrodynamic limit. We talked about how the Boltzmann equation describes how all those particles behave statistically, and how this paper really takes it up a notch.
Yeah.
Proving its validity for, any time scale.
For any length of time, it's impressive.
We even went through those fascinating concepts like long bonds and that cutting algorithm,
Right.
which really help us analyze those complex particle interactions on a torus, that donut shape.
Exactly, it's all connected.
And then we even got into that mind-bending idea of how time can't be reversed in fluids, even though the individual particles follow reversible laws, with entropy maybe playing a key role there.
Really gets you thinking, doesn't it?
It does. Okay, so let's zoom out a bit now. What are the bigger implications of this research? Why should our listeners, the AI researchers and ML engineers, care about all of this?
That's the important question, right? This research might seem like super deep in theoretical physics,
Yeah.
but it goes way beyond just fluids. It's about understanding complex systems, any complex system.
So it's not just about modeling water flowing or air flowing, it's about how complex behavior emerges from simple interactions.
Exactly. This has the potential to change how we approach a ton of challenges in AI and other fields. Think about it, financial markets, ecosystems, social networks.
Why, they all have these tons of individual agents interacting.
Exactly. And maybe we can use these same mathematical tools to understand and model those systems.
So you're saying we could use this for things like, I don't know, modeling the spread of information on social media.
Yeah, think of each user as a particle and their interactions as collisions. We could analyze those patterns and use techniques like in this paper to understand how information flows, identify influential users, even predict trends.
That's wild, like we're using fluid dynamics for information.
It's not a completely new idea. We've seen it in network science and statistical mechanics, but this paper takes it to a whole new level, really.
It's really exciting, but there have to be some limitations, right? Real-world systems are messy.
Of course, real-world systems are way more complex than those perfect particle systems they studied. Human behavior, for example. It's driven by emotions, beliefs, things that are hard to put into math.
So it's not like a magic formula we can apply everywhere.
No, it's more about giving us new tools, new ways of thinking about these problems.
More about inspiration and changing our perspective.
Exactly. This paper shows how powerful math can be, how it can have real-world implications for understanding everything around us. Sometimes those big insights come from unexpected places.
So don't be afraid to explore outside your comfort zone.
Exactly. That's where the real breakthroughs happen.
This paper is a testament to that, to collaboration and human ingenuity, solving these age-old challenges with fresh ideas and new approaches.
It's been great discussing this with you. It really makes you appreciate the power of research like this.
Absolutely, and I hope our listeners feel the same way. This was a wild ride.
It was.
And that concludes our deep dive into this incredible paper. Thanks for joining us on this intellectual journey.